Find the length of the leg of a right triangle with a leg length of 6 meters and a hypotenuse of 10 meters. So we are definitely missing a leg there. So that means that we are going to need Pythagorean theorem. So I've got my Pythagorean theorem right here. And we'll just apply the values that they gave us. So starting with this leg length of 6 meters, I'm going to make it the first leg, although you can make the second one if you'd like. And then the hypotenuse is saying that it's 10 meters, so I'm going to make the hypotenuse 10. And then we just apply the rest of the Pythagorean theorem. So we got 6 squared plus the other leg squared equals 10 squared. From here, all we got to do is solve this, and we're going to start with just getting rid of those exponents. So evaluating 6 to the power of 2, which is 6 times 6, that's 36. 10 to the power of 2 is 10 times 10, which is 100. Now we have 36 plus the other leg squared equals 100. So we're at the point where we're going to need principles of equality in order to get this leg squared all by itself. So I can't have the 36 with it, so I'm going to have to zero that out by subtracting 36. If I do it to one side, I must do it to the other side, so that zeroes that out. We already dropped leg squared like we wanted, so that it's all by itself. And then 100 minus 36 is going to give us 64. Now that's a leg to the power of 2. We also do not want a leg to the power of 2. We want this to show as just a leg. So in order to get rid of that exponent of 2, I'm simply going to take the leg to the power of 2 and square root it. But again, this is also a principle of equality. If I do it to one side, I must do it to the other side as well. So 1 number times itself is 64. It's 8. So the second leg, or the missing leg, we just found, the value is 8. We'll label it in meters, and that's it. So that's using the Pythagorean theorem to find a leg. Today, we're going to be using the Pythagorean theorem for pretty much the same idea, but we're going to have to do some thinking as well. We'll be applying it to different situations. So our first objective, I can find a missing length on any right triangle. So that means legs or hypotenuse. And then I can find the distance between 2 points on a coordinate grid, which is going to make a right triangle for us, so that we can use the Pythagorean theorem. And then I can use the converse of the Pythagorean theorem to classify triangle lengths. So take a minute, copy that down, then we'll get started. So we've already seen this before. A leg squared plus leg squared is the hypotenuse squared, but this only applies to right triangles. So if they give us something that is not a right triangle, then we can't use the Pythagorean theorem. But we can use, like we saw in the objective, the Pythagorean theorem in order to determine and classify triangles, which we will be doing today. So we've seen it like this. We worked with this formula last time, but if you'd like to see it as a squared plus b squared equals c squared, you can. Either way, we'll end up using principles of equality in order of operations to solve, which means that having a calculator will be very handy because it's going to simplify a lot of the work for us. So yeah, the two legs make up the right angle, and it's not showing in this picture, but the right angle would be shown right here. That's a right angle, and we know that right angles are 90 degrees. Again, we went over this last time, but it's good to see it once in a while as well, just as a quick review. So this one, again, we're just going to be applying the Pythagorean theorem. What is the length of the dotted line in the diagram below? Leave your answer in simplest radical form. All right, so we got, well, there's kind of 3 triangles right here. First off, let's look. Okay, so I have this, we're going to call this a rectangle. It kind of looks like a square, but we can't guarantee that it is going to be a square. Which means we've got to look at this triangle right here. All right, now I'm going to take this triangle and separate it. Let's see if I can do that. That's okay. And we can see, based on where that right angle is, we have 2 legs. We got a leg that's 4 and a leg that's 8. So I'm going to have to take this triangle, and I'm going to have to solve for the hypotenuse. Once I have this value, the hypotenuse, then I will have this length of this rectangle. Now, if that doesn't make sense what we're going to be doing after that, that's okay. We're going to go over it. Let's take a look at this. So we got this triangle here. space though. There we go. Okay, so my first leg is, I'll say that's 4, and then the second leg is 8. We are solving for the hypotenuse. So that would be 4 squared plus 8 squared is going to equal the hypotenuse squared. Like this, if you want to evaluate each part, 4 to the power of 2 is 16. 8 to the power of 2 is 64. And when we add these together, we should get the hypotenuse as a square. Now combining these, looks like we get 80 equals the hypotenuse as a square. Like we've seen, we don't want the hypotenuse as a square. We just want, in the end, the hypotenuse. Now this is just the hypotenuse for this triangle. There's going to be others that we need to consider. But since I want that hypotenuse, I'm going to have to take that hypotenuse to the power of 2 and square root it. But if I do that to one side, I've got to do the other side. And I'm going to round this, it says, to leave your answer in simplest radical form. So I guess we might have to do that. So start out, I'm gonna take the square root. So remember the top left, we got second and then the x squared button because that's where the square root symbol is. And then I will type 80 and then I can push enter. And when I do, I get this decimal. Okay, and that's pretty good. It's just that it's not simplest radical form. Okay, so that means that we're going to look at this square root of 80 right there, and I'm actually going to leave that alone as the square root of 80. Well, let's see. So another way to do this, especially since we're not looking for the answer right now, is instead of writing this decimal, I'm going to write it simply as the square root of 80. Now that isn't fully simplified, but we're going to see if it needs to be simplified. So we're not going to worry about the simplification process right now. But what I know now is that for the triangle that we broke off right here, let's see if I can do that better. This one, it wasn't much better, but that hypotenuse is the square root of 80, which we know is about 8.944279191. Which means that this length right here on our original figure is also the square root of 80, which is more exact than 8.944279191. But now that I have this length right here, this is a rectangle, meaning that this length also is going to be the square root of 80. Now I'm putting this here, even though we don't necessarily need it there. Because by taking this rectangle and splitting it in half this way, from corner to corner, what we do is we create 2 congruent triangles right there. So it doesn't matter which triangle you want to use. It's really up to you. I'll use that. I'll use this one right here. Okay. So we're going to take that half rectangle, and we're just going to look at this part of the rectangle, half of it cut from corner to corner, which gives us this triangle. So I can see that my purple length, which is now become a leg, is at the square root of 80. It gave us this length right here, which is 10. So that's going to be equivalent to this one right here, because opposite sides of rectangles are the same. And so this length is 10. Which means that for this problem, we are trying to find this hypotenuse, which is what it was asking for in the first place. We want to find the length of this dotted line. So we're back to the Pythagorean theorem. So we used the Pythagorean theorem once for the original triangle, but now we're using the Pythagorean theorem for this triangle. And even in the original figure, we're showing this right angle mark right here, 90 degrees. So we know that we can use the Pythagorean theorem, but we have 2 legs. I've got one leg that is showing as the square root of 80. The other leg is showing as the value 10. What we don't have is the hypotenuse. So we're going to take that square root of 80 and square it, which we can do in the calculator, plus 10 to the power of 2, and this would equal the hypotenuse to the power of 2. So we'll use the calculator once again for this, and we'll see what it gives us. All right, the square root of 80 to the power of 2, that's just going to be 80, because the exponent 2 and then the square root are going to essentially undo each other, but you can say cancel each other out. 10 to the power of 2, 10 times 10 is 100. When I add these numbers together, I get the hypotenuse to the power of 2. And by combining these, we've got 80 plus 100, which is 180. this is the hypotenuse to the power of 2. What I would like, though, just like we had before, is not the hypotenuse to the power of 2, but just the regular old-fashioned hypotenuse. So I'm going to take that hypotenuse to the power of 2 and square root it. And if I do that to one side, I must do it to the other side as well. So once again, the calculator is going to give us, a pretty ugly looking number. Okay, this is the decimal value that we do not want. That is garbage. Because up there at the top, it says that we want to leave the answer in simplest radical form. Now we could simplify this if we wanted to, and in fact I will do that, just to show you how much fun it is. Okay, so I'm going to go back to the square root of 180, where we square rooted, to get the hypotenuse, because the hypotenuse itself is the same as taking the square root of 180. So this goes back to 8th grade stuff, which we've probably forgotten, and that's okay, because we're going to review it right now. So what I'm going to do is take the square root of 180. I'm just looking at the 180, and I'd like to factor it, meaning I'm looking for values that I can divide it by, specifically that are perfect squares, such as 1, 4, 9, 16, 25, and so forth. So I look at this one. Looks like we could divide it by 9. Let's see what happens when we do that. So that'd be 180. 2 factors would be something like 9 and 20. And you can use a calculator for that. But I don't want to do that. We can do more. We can do more with that. So it looks like we could do, if I were to divide it by 36, it'd be 36 and 5. Yeah, that looks better. You could have used, if you wanted to, the factors of 4 and 45, it looks like. But again, that's not going to help us right there. Because we want the biggest factor of 180 that is a perfect square. Now that may take some guess and test right there. Again, I'm just kind of showing you how awesome this is. We want the biggest one, so we're going to take the square root of 180, and instead of showing it as the square root of 180, we're going to show it as the product of 2 factors, such as 36 and 5. 36 again, because it is the biggest perfect square factor of 180. Now we can take the square root of 36, which is 6. Almost put 4. And then the square root of 5 just stays the square root of 5. And this right there is the hypotenuse, which is also the length of this dashed line right there. Okay, so that's my answer in simplest radical form. Now let's say that you didn't really enjoy that process, which is pretty common, because, I don't know, most people your age don't like this stuff. The other method is to use a calculator, which I have. Not these ones, though, not the TI-84s, because I don't know how to make these TI-84s do it, but I do know how to make a TI-30XS do it, which is the multi-views. If you want one of these, just let me know, but let me finish this. So in this calculator, I push second x squared again, and then I just type in the number, 180, I push enter, and this calculator says, I mean, you'll never believe it, but it says 6 times the square root of 5. Now, it's not showing the multiplication, but it's there. It says 6 times the square root of 5. I didn't have to do any of this work right here, as fun as it was. It's just done. Okay, so again, this 6 times the square root of 5, which we already know is 13.41640,786. That's this length right here. We found it both in decimal format and in its simplest radical form, which would also be another way to say we want the exact value. All right, for this one, we're going to solve for x as well. So we're going to look at a couple parts of this shape right here. And remember, the idea is that we're looking to make a triangle. We're looking at this one right here. And so what I'm going to do is I'm going to take this side length right here, which I know is 3. And I'm also going to look at, well, we'll say this side length right here, which is 1. Okay, now it's important that we have this information down in order to find the length of this x, which is the hypotenuse for the triangle that I'm looking at right here, right? So remembering that this red length here is 3 and this green one is 1, what I can do is take this red length right here and just move it up right there. And then I know that this red length is 3. Now the problem is, right now we have this whole side length, which is 3. But what I know is if I take this green side length and move it here, it had a value that was 1, so that's going to be 1, which means that the rest of that side length here, altogether it was 3, but we used up one of them, which means that the rest of it would be 2. Okay, so this 1 side length and this 2 side length totals up 3, which is the full side length right there. Now I have my right triangle here, which I can solve for. And in fact, if I wanted to, I could take that bottom part, just in case if it's in the way, I could get rid of it. What I'm going to do, though, is I'm going to split it off. So this is the triangle that I'm looking at right here. And we're solving for that x side length right here. So I drew that by hand, so of course it kind of stinks right there. But what we have up here at the top, of course, is our Pythagorean theorem, because we are looking at a right triangle. Again, I'm pretty much ignoring what I had in the beginning, because this triangle right here is the same as this triangle, which we have made. So from there, we have one of the legs of that right triangle is 2. The other leg is 3. And then what we're looking for is the hypotenuse. I'm just going to keep that as hypotenuse. I mean, you could write in an x right there, but I'm not going to do that. So now I have leg squared plus leg squared equals the hypotenuse as a square. Now what I'm going to do, I'm going to do this a little different. Okay, so what I'm going to do, I'm going to take both sides right now and square root both sides. So I'm going to square root the hypotenuse to the power of 2. And then I'm going to show you that you can do this directly in the calculator. So I'm going to push second x squared. So that's going to give me the square root button on my calculator. And on the calculator would look something like this. And then as I type values in, it's going to get longer, but I'm going to write 2 to the power of 2 plus 3 to the power of 2. It's going to make so I can skip a lot of that, a lot of the work here. 2 to the power of 2 is 4, 3 to the power of 2 is 9 kind of stuff. And then once I get that solved, I will have just the hypotenuse in the end, which is what I do want from this. So square rooting both sides, it's going to make so we can skip some of that work. Here's what my calculator gave me. So it's a pretty nasty decimal, and it's okay to have a decimal answer, but as it turns out in this problem, what we want is the answer in simplest radical form. So this is where a TI-30 XS multi-view would come in pretty handy. And if you do, you're going to get the square root of 13. Pretty much all you do is take 2 to the power of 2, which is 4, 3 to the power of 2, which is 9, 4 plus 9 is 13. So if you need to show that work, that's fine. 13 is prime, so this cannot be simplified any further, so there's no need to worry about this simplified radical form business. We have that hypotenuse, which is, you know, if you wanted to show that as x, you could as well. But square root of 13 is what we're looking for on this one. So we're going to solve for x on this. And we see two triangles. This, whatever the shape is, some kind of quadrilateral. It's been cut right here from corner to corner, making these two triangles, which is very convenient because we have a right angle here and a right angle there. Since we're seeing right angles, we should be expecting to use the Pythagorean theorem. And since we love to do it, that hopefully, you know, it's not too bad. So first off, I got this leg and this leg right here. And sorry, my lines aren't very straight, but we know these are legs because they make up the right angle right there in that first triangle, and then we have this hypotenuse right here. So the two values that they gave us were a leg, which I'm going to just make the first leg once again. So you might do a better 6, and that wasn't very much better, but the hypotenuse is 9. So we have a leg of 6, a hypotenuse that is 9. So we're going to take 6 to the power of 2, and we're going to add the leg squared there. And that should equal 9, the hypotenuse, squared as well. So just old-fashioned evaluation here. So we can use the calculator. 6 to the power of 2 is 36. And 9 to the power of 2 is 81. 9 times 9. So now we have this new equation. 36 plus the leg squared equals 81. And we're pretty close to getting this leg, at least leg squared even. But we're going to use the principle of equality now to solve for the leg squared, which is hopefully going to help us to solve for the leg. So I don't want that 36 with it, so I'm going to have to zero that out by subtracting 36. All right, so this is what happens. The 36 zeroes out. That's part of the plan. We've zeroed out the leg squared. 81 minus 36. When I did this in the calculator, Give me 45. Now that's a leg squared. If we wanted just the leg, which may or may not be helpful, but I'd have a leg. If I wanted it, I would have to square root both sides there, like this. And the square root of 45, we're just going to keep it as the square root of 45. If you'd like to see the simplified square root there, you can. For example, again, we'll look at the two factors of 45, such as 9 and 5. I'm using 9 specifically because it's the largest perfect square factor of 45. And then if we were to square root those, the square root of 9 is 3, and then the square root of 5 just is the square root of 5. So either the square root of 45 or 3 times the square root of 5. I'm going to keep the square root of 45 right here just because I'm going to need it. I'm going to need that. Plus, it's easier to type than 3 times the square root of 5. So we just found then this length, this thing, I'll do it in orange there, this other leg right here, as the square root of 45. Which means now that we can look just at this triangle right here, right? We've already figured out this triangle. If we want to ignore it, well, then we can. In fact, I'll redraw that triangle just to make this hopefully a little bit easier to see. So right now we got something that looks like this. And we're all going to pretend like my drawings are good. So yes, it did give us the right angle there. We got this right angle, which means I'm looking at this leg right here that's 5. The other leg is an x, but we have a hypotenuse that's the square root of 45, which used to be the leg of the first triangle. And again, if you want 3 times the square root of 5, that's fine too. So we'll solve for this one pretty much the same way as that last one because we are solving for a leg once again. So we're going to go back to the Pythagorean theorem. And we love it so much that it's good to see it again. There it is. All right. So I'm going to take this Pythagorean theorem. I have one of the legs of this new triangle, which is 5. A hypotenuse, which I have in orange as the square root of 45. And again, this is why keeping this in a square root format like this without having to simplify it back here is good because we're going to square that square root, which is going to undo it. So now we've got 5 to the power of 2 plus the leg squared, the other leg squared, is going to equal that square root of 45. And you can just put the power of 2. If you want to put it in parentheses, that's fine too. But the calculator is going to find it either way, even though I'm not going to use a calculator for it. So 5 to the power of 2, 5 times 5 is 25. This is going to be added to the leg squared, which will equal the square root of 45 to the power of 2. Again, it's just going to be 45 right there. Okay, because the exponent will undo the square root. That's it. So now we have this equation to solve. And we're going to use some principles of equality because what I'd like right now is take that leg squared and get it by itself, meaning I don't want the 25 there. I'm going to have to zero it out by subtracting 25. So leg squared then, because we did zero that out and dropped the leg squared. 45 minus 25 is 20. So 20 is not a perfect square. And I'm saying that because the next step is to take that leg squared and just make it a regular leg. And that will be the value of x. And which, by the way, if you wanted to make that an x, you could have. But in order to make this leg squared a leg, I'm going to take it and square root it. So I'm going to square root 20. So I'm going to show it as the square root of 20. Again, as a decimal, it was pretty ugly. The square root of 20, enter 4.472135955. We don't want that ugly decimal. What we want is the, I guess they didn't say, round to the nearest tenth. Oh, I guess we do. Okay, well, fair enough. The leg then, according to my calculator, is showing as 4.472135955. So that's the ugly decimal. What we want is the rounded decimal. 2 at the top, it says to the nearest tenth. So the tenth is where the 4 is. To the right is a 7. Since it's 5 or more, we're going to have to add 1 to the 4, making this leg in the end 4.5. And I don't see any labels there. and that's okay. So just to see if you want to do this by hand, which not many people do, but since I do, I'm going to show it. So the square root of 20, if I were to look at the factors of the square root of 20, the biggest factor of 20 that's a perfect square is 4. So that'd be 4 times 5. I would take the square root of both of these. The square root of 4 is 2, and then we just got that multiplied by the square root of 5. We wouldn't make this any simpler because the 5 is not a perfect square, and it doesn't have any factors that are perfect squares. So this value, or the square root of 20, would simplify here if we needed the answer in radical form. Radical just means it's got the square root, but we did it over here with the rounding, and that's pretty good. Next up, we're going to classify triangles by angles. And right now we're looking at right triangles, which is nice. Of course, a triangle only has 180 degrees inside it, which you learned in 7th grade, but probably don't remember, and that's all right. An acute triangle is where all 3 angles in the triangle are less than 90 degrees. And obtuse is where one of the angles is more than 90 degrees. Of course, you can't have 2 angles that are 90 or more than 90 degrees, because then you'd have something more than 180 degrees. So we're just looking at classifying by angles. We got acute, right, and obtuse. That's it. That's the only 3 options that we got. But we can also classify by side lengths. I guess comparing side lengths. Now, the thing about this, what we're seeing on this slide, is it says the converse of the Pythagorean theorem, which is one of our objectives. What we're trying to figure out is if the 3 lengths that they give us, if we find that the leg squared plus the leg squared is the hypotenuse squared, if it actually equals it, just like we've been seeing, then we know we have a right triangle. So it's kind of backwards, where the Pythagorean theorem says, if you have a right triangle, then leg squared plus leg squared is a hypotenuse squared. We're doing it backwards. We're saying, that's why it's a converse, it's backwards. We're now saying, if I can find that we got a leg squared plus a leg squared is the hypotenuse squared, then I know I have a right triangle. So it works both ways. But on the other hand, let's say that the leg squared plus the leg squared is bigger than the hypotenuse. If that happens, then we have an acute triangle. And if we find that the leg squared plus leg squared is the hypotenuse is less than the hypotenuse squared, then it's obtuse triangle. Meaning that, in fact, for this one, where it's the legs, the square of the sum of the legs is greater than the hypotenuse squared, or where the sum of the squares of the legs is less than the hypotenuse squared, those are not right triangles any longer. Now, what they're going to do is they're going to give us 3 numbers, and they're probably going to mix these up for us, which is okay. If we look at the numbers, all we're looking for is the biggest of the 3 numbers, the biggest of the 3. Why are we looking for the biggest? Because the biggest one is the hypotenuse. The other 2 have to be legs. That's it. For right triangles, or pretty much any triangle, but right triangles specifically, biggest or longest length of the triangle will be the hypotenuse. We look at a problem like this one. These numbers are already listed in order from least to greatest, 39, 52, 65. Which means that the first 2 numbers, 39 and 52, are legs. Now, is that always going to be the case where these are listed in order from least to greatest? That is not always going to be the case. So you got to be careful and look at the numbers, figure out which one's the biggest. The biggest one will be the hypotenuse no matter where it is in the list. So I say I've got a leg squared plus leg squared. I've got a leg that's 39. I've got another leg that's 52. And I've got a hypotenuse that's 65. If I were to square the legs, add them together. Now, I'm not going to fill in the blank here because I don't know if it's going to equal or if it's going to be less than or greater than. But I can't take the 65 to the power of 2. So I don't know these values off the top of my head. And if you do, that's pretty impressive. I just don't have it. But 39 to the power of 2 is going to be 1,521, just using a calculator there. 52 to the power of 2, 2,704. And 65 to the power of 2 is 4,225. Now again, I have no idea if I add these together if it will equal 4,225 or if it will be greater than or less than. So I'm going to add those 2 numbers together 1,521 plus 2,704. Enter. I'm just putting that in my calculator. So when I add these two numbers together, I got 4,225. Now, I didn't know that was going to happen, but I know that 65 to the power of 2 is also 4,225. I have an equal sign here. In fact, so since these are equal, now I know that I have a right triangle. Okay, because the sum of the squares of the legs is exactly the same as the hypotenuse as a square as well. That's it. That's all we got to do. Let's do this one right here. So once again, the numbers on this one are not in order from least to greatest, which we got to be careful about because that's what can trip up students, and it has in the past. My biggest number here is 53. I don't really care how 28 and 44 compare to each other. I just know that the biggest number is 53, so it must be my hypotenuse. The first leg for me then is going to be 28, so I'm just going in order from left to right, and then the second one is going to be 44. Now again, I can't really compare these, so I can put a question mark there in the middle. So we got 28 to the power of 2 plus 44 to the power of 2, and we don't know how that's going to compare with 53 to the power of 2. But my calculator is going to help me with this. So I got 28 squared, which is showing as 784. I've got 44 squared, which is 1,936. And then finally 53 squared, which is showing as 2,809. I'll tell you this right now. I can see in the ones place value of 4 plus a 6 is going to be 10, which is not exactly 9. So right now, I know that it's not going to be equal, meaning I know that it's not going to be a right triangle. Let's keep the comparison going here. We've got a question mark there. Let's go and add these two numbers together. So 784 plus 1936. Okay, so I got 2,720. And I'm going to compare this with 2,809. All right, so the sum of the legs, sum of the squares of the legs, is less than 2,809. Okay? So, since the sum of the squares of the legs is less than 2,809, this means that the triangle that we would be looking at, if we were to make it, would be obtuse. Now, just so you understand, I don't have that memorized, so I was using it for the color, but also to refer back to the chart. And if you don't have this memorized, that's okay too. Just refer to the chart. So for this problem, we have 2 legs and a hypotenuse. Of course, the hypotenuse is the biggest number, which in this case is the first number. Is 80 is the biggest number. So just remember, these are not always going to be in order from least to greatest. I have one leg that's 65. Doesn't matter which one I make that leg. And the 48 is just the other one right there. So again, I'm putting a question mark here in the middle because I don't know if it's going to be equal to, greater than, or less than. Then we just fill in everything else. 65 squared plus 48 squared. We don't know how it compares to 80 squared, but I'm just going to go straight to my calculator and then do these. So 65 squared, my calculator gives me 4,225. 48 squared shows as 2,304. And then 8 squared should be 80 squared rather, should be 6,400, and it is. So this is what we get, and I'm going to add these two numbers together and then compare that with 6,400. So let's go ahead and combine these together. So we've got 2,304 plus 4,225. Enter, and I get 6,529. Now what I'm seeing from a few slides back there was that I've got the sum of the squares of the legs. This number is going to be bigger, so I don't really need that question mark in there. They're definitely not equal, so I know I'm definitely not looking at a right triangle because they're not equal. And then I see here that 6,529 is bigger. So my legs, sum of the squares of the legs is bigger, which means I'm looking at an acute triangle for this particular problem. This one's going to work pretty much the same way. We just got to set this up. Again, we don't know how it's going to compare. The sum of the squares of the legs is going to compare with the hypotenuse, but I do see that my biggest side length is 41. That's the first one I would find if I were you, but you don't necessarily have to, but I do it just so I don't get mixed up. So my first leg I'm going to say is 40. The second leg I'm going to say is 9. We're going to square these, add them up, and compare that with 41 to the power of 2. So I'll keep a question mark there in the middle. So 40 to the power of 2, 40 times 40 is going to be 1,600. 9 to the power of 2, 9 times 9 is 81. And then in my calculator, I just do 41 to the power of 2, and I get 1,681. So we're going to compare these values. And so we don't have to do anything else with 1,681, but what I can do here is combine the 1,600 plus the 81, thus the squares of the legs, right? That's going to give me 1,681. So as it turns out, the values that we have here are exactly the same, right? So I can throw in there an equal sign, and we know if they are exactly the same, meaning equal, that means that we know we are looking at a right triangle. You could make if you had lengths of a triangle that were like this, you would in fact have a right triangle. So graphs, 2 points, and right triangles. 2 points on a grid will make a hypotenuse of a right triangle. Use the grid lines to make legs. Okay, so here's what this is talking about, is they're going to give us 2 points that, I mean, they're not going to be put, well, maybe they will put them on a graph. Maybe we got to put them on the graph. I don't know. But let's say that we got this point, let's say this one right here, which is at 6, 8. And let's use, I'm going to make this one kind of far away. We'll make it right here. And this one's at -9, -2. Okay. Now, I don't really care about the ordered pairs on this, so long as I have a graph. But what happens is if I were to take those 2 points, and if I were to connect them, and I'm going to use a technology for this because, as you guys have seen, my straight lines are not very straight at all. That would be a hypotenuse. Why is it a hypotenuse? Well, it's diagonal, which should kind of be a first indicator that it would be. But it's also going to create a triangle as if I were to look at these lines as streets, which we've talked about in the past, and I end up with something like this. This is a right triangle. In fact, even though they're not trying to show this specifically, but that's a right angle right there. So I'm using one of the boxes to show that I do have a right triangle. Okay, what I'm missing here is all 3 lengths. I'm missing all 3 lengths, okay? But I can figure out what those are. So if I were to look at the right leg right here, the red leg length, I can just count how many boxes that is to figure out how long that is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's convenient, 10. And then the other length. So again, I'm just going to count boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15. So I have 2 legs. And if I wanted to use the Pythagorean theorem, which I would want to do, probably not everyone, but I would. But I can take that. There's my Pythagorean theorem. There. Now I can take my Pythagorean theorem. I can replace the legs, square root them, and then find the hypotenuse as, well, just the hypotenuse, really. Okay, we're not going to do this example because we got other ones. But at least that's how it sets up. Graph a right triangle with the 2 points forming the hypotenuse, which we've seen. Using the sides, find the distance between the 2 points to the nearest tenth if necessary. So we are not writing these in radical form. There we go. So I'm going to start with -7, 2. So I find from the origin to the left 7 up 2. So that's going to be this point right there. Now if you want to label it as -7, 2, that's fine. You don't necessarily have to. But at least I've got the first one on there. The next one is going to be -4, -2. So I would go to left 4, down 2. Which is going to give me this point right here. Again, I'm going to label it even though you don't necessarily have to. Just trying to be thorough here. So the way that I've done my triangles is if I wanted to make a hypotenuse, I've been trying to make these purple, even though it hasn't worked all the time today. Okay, so it's kind of like driving from this location to this one, and these are streets that you got to go down, and we can only go left or right and then up and down at a time. Doesn't necessarily have to be in that order. But here's what I'm going to do. I'm going to start from this point. I'm going to go to the left, and then I'm going to go up. There is my triangle right there. And once again, they have shown us, even though we may not consider it such, but that's a right angle mark right there, showing us that we do have a triangle. So from there, because I do want the Pythagorean theorem, I've got to count the length. So that's 1, 2, 3, 4. So that's a length of 4 for that leg. And then the other leg, 1, 2, 3, boom, 3. Now, if you were nerdy like I am, then you would have Pythagorean triples memorized. This isn't really something I'm proud of. But you would know right now that this answer is going to be 5. You have to know that. Of course you don't. But that triangle, this triangle, a 3, 4, 5 triangle is a very common Pythagorean triple. So if you never see it again, that's fine. But some of you may, depending on what you do later in life. So let's use the Pythagorean theorem to figure out why this is 5. Okay, so my first leg I'm going to say is the 4, although you could make it 3. The second leg I'll make 3. And if I take the 4 to the power of 2 and add 3 to the power of 2, it's going to be the same as the hypotenuse, also to the power of 2 as a square. So, evaluating these, 4 to the power of 2 is 16. 3 to the power of 2 is 9, 3 times 3. So 16 plus 9 is going to be equal to the hypotenuse as a square. And then 16 plus 9 is going to be 25. Some of you guys, I think, see how that's going to be 5 already. But now, what I will do is square root both sides to make just the hypotenuse. Right? Not hypotenuse squared. Square root of 25 is 5. It could be negative 5, but we don't really care about that. So 5 will work. We just want the positive values there. So we got the hypotenuse is 5, just like I said it would be because of this Pythagorean triple. Another Pythagorean triple that's pretty common, I think it's 3, 12, 13 triangle, but I also assume you don't care. Now, just to emphasize what we saw in the last lesson, because you could do this if you wanted to, is back here, at this point, you could have typed this whole stuff into the calculator and avoid these steps. So if you wanted to, you could have just typed in the square root of, at this point, you could have taken the square roots of both sides. And you would have had the square root of 4 squared plus 3 squared. You push enter, and the calculator would give you directly 5. And it said up the top, round to the nearest tenth. It wasn't necessary, so we got to skip the rounding part. Let's get to work on this one. So first up, we're going to find the right triangle by graphing these 2 points down here. When we find the distance, we'll round to the nearest tenth if it's necessary. But to start us off, I'm going to put this first ordered pair here at -1, -4. So from the origin, left 1, down 4. We got a point right there. And I'll label it as -1, -4, not that you have to. And then I'll put the second one on there. So from the origin, 1 to the right, 3 up. 1, 3 at this location. And from there, we can make a triangle. Now, there's 2 ways to make a triangle. On the last problem, I kind of did a triangle beneath the points, but you can do one above as well. So I'll show that to you. First, I'm going to connect those points to show that we have, in fact, created a hypotenuse. But what we're missing then are the 2 legs. So again, I would go from one point to the next. I'll go from left to right. Again, it doesn't really matter. But what you should notice is that the boxes within the graph, the grid, are going to make a right angle for you, just so you know that you are, in fact, looking at a right triangle. So I'm going to start with this one on the left, the red line, the leg. 1, 2, 3, 4, 5, 6, 7. So that's a length of 7 there. And then the one on the top there is 2. So 7 and 2. Now we're going to go to the Pythagorean theorem. So let's get that on the screen. There we go. And one of my legs is 7. The other leg is 2. We don't know the value of the hypotenuse. But what I can do is take the legs, square them, add them together, and I know that would give me the hypotenuse as a square as well. So this one's got rounding, so I mean you could take the square root of both sides at this point, but I'm going to do this part by part. 7 to the power of 2 gives me 49, 7 times 7. 2 times 2, or 2 to the power of 2, is 4. So again, we're going to add these together, and that should be the hypotenuse as a square. Now I will go ahead and combine these two values. So that'll give us 49 plus 4, which is going to be 53. Now that's the hypotenuse as a square. It's the area of the square. If you were to look at the hypotenuse, we want just the side length of the hypotenuse. So at this point, I'm going to take the square root of both sides. And that is going to give me the hypotenuse, just the hypotenuse, not the hypotenuse as a square. And this is the number that I get. Okay, now that decimal, it's large. Not that that really matters. But what I want to do at this point is I want to round to the nearest tenth. So the nearest tenth is where the 2 is right there. To the right, the 8 is 5 or more, so I'm going to have to add 1 to that 2, making my final answer a 7.3 value. Now there's no units attached, but what I have now is the hypotenuse that has been rounded to the nearest tenth, and that's as far as I need to go. All right, there's the 3 objectives for the day. If you feel pretty good about those, the assignment will go well. If they didn't make any sense, you need to be asking questions, maybe rewatching the video, it's up to you. But you got plenty of help. Good luck.